we're going to see how to solve Kohn-Sham equations. But we're going to see that how it's done practically. So we're going to describe the practical calculation of these Kohn-Sham equations. And for that, it's very important the concept of a basis. We need to specify the basis in order to expand these Kohn-Sham orbitals. But we'll see that later. So first, let's start with the Kohn-Sham equations. Which were the Kohn-Sham equations? These are the Kohn-Sham equations that we need to solve. Okay, here we have, that's the kinetic energy, we have the external potential, we have the Hartree exchange and correlation potential, and these are the Kohn-Sham orbitals, these are the energies. And actually, the sum of the external potential and the Hartree exchange and correlation potential is usually called the Kohn-Sham potential. So these are the equations that we want to solve. In order to write it in a more condensed way, we are going to call all of this, as it looks very similar to the Hamiltonian, actually it's the Hamiltonian of these effective electrons of the Kohn-Sham system, we are going to call it H. So the H operator is going to be applied to the Kohn-Sham orbitals in order to get the eigenvalues times the Kohn-Sham orbitals. So these are the equations that we want to solve. How we are going to do that, how it's done practically. So of course using the computers, because this is the only way of getting, there's no way to get in a general way to get in analytical solutions for that. We need to apply numerics, we need to apply the computers in order to solve these orbitals. So for that we are going to start by expanding the Kohn-Sham orbitals in a generic basis, and this is the basis that we are going to consider. So in this case, beta is going from 1 to m. We have m elements in this basis. And what is that generic basis that the one that we are considering? Of course, there are many different possibilities, different ways, different kind of basis that people is considered in order to do this expansion. You have plane waves. This is one possibility that is very commonly used in physics, for example. But you also have other possibilities like atom-centered bases or atomic orbitals, which actually this one is the one giving the approximation, which is called the linear combination of atomic orbitals. That is very often used in order to describe the molecules. And actually this approximation is, the philosophy of this approximation is the one which is actually behind the tight binding models that are also used a lot in physics. So here we have the expansion of the Kohn-Sham orbitals here in the basis that we have considered. So basically here we are going to, in this here we are not going to specify which kind of basis that we are using, and we are going to describe the practical calculation considered for any generic basis. So this is the expansion we have for the Kohn-Sham orbitals here. Okay, now what we are going to do is we are going to insert this expansion here in the Kohn-Sham equations here. And then, once we have done that, we are going to multiply on the left from here by this phi alpha complex conjugate, and then we integrate that over r prime. We integrate over r. And if we do that, we arrived to the following expression. That's the following expression we have after doing that. This is the one. Okay? Where here we have different elements, and now we are going to see which are the different elements arising in this equation here. So first of all, this one, H alpha beta, is this one. This is the one. So as you can see here, these H alpha beta are basically the matrix elements of this Hamiltonian operator in the Kohn-Sham equation, considering the basis, the generic basis we have considered before. Okay, this is this H alpha beta. We know that this C beta is just basically the expansion coefficients we have for the Kohn-Sham orbitals. This is the eigenvalue, and then this is alpha beta is this one, which are basically the scalar product of phi alpha and phi beta. And if they are not orthogonal, of course, they don't have to be zero. So this contribution is basically saying the elements of the overlap matrix of the basis function. That's in order to take into account possible non-orthogonality of basis orbitals. So if we write this equation here in a more condensed form using the matrix notation, we can write it in this way here. Where now we're going to describe which are the different matrices arising in this equation here. Okay, this is writing the same equation in a more condensed form considering the matrices. So again, this H here, this H matrix is the Kohn-Sham Hamiltonian matrix, which can be expressed in this way here. It's an M times M matrix because we are considering M elements in the basis. Okay. Then these C are the eigenvectors written as a column. So these are the eigenvectors, basically is the expansion coefficients of the wave functions of the Kohn-Sham orbitals. So it's written as a column here. Equal to epsilon, which is the eigenvalue. And this overlap matrix is writing in here we have again, which is M times M matrix again. For example, if the elements in the basis are normalized, we have that the elements on the diagonal are 1. And if they are not orthogonal, you can see that the elements of the diagonal, they are not going to be 0. Of course, if the elements in the basis are orthogonal, then orthonormal, then that's going to be the unity. And we don't have to take into account that matrix, that overlap matrix, because that's going to be the identity matrix. And then the C again is going to be the eigenvectors written as a column. So here, consider once we have specified the matrix, the basis we have, as the expression of the Kohn-Sham equation, the Hamiltonian is known, then we have that this matrix is, you can calculate that matrix here. And besides that, this overlap matrix also, you can calculate that. So here, which is unknown, and this is what we want to solve in order to solving that equations here, this is the eigenvector column here is what's not known, and this eigenvalue is not known either. So this equation system is the one that we need to solve in order to calculate either the eigenvectors and the eigenvalues. Of course, as we have m equations here, we could have m eigenvalues here from here, and from each eigenvalue we can get the corresponding eigenvector. Okay, this is the usual procedure that in practical calculation of the Kohn-Sham equations is considered in order to get the Kohn-Sham orbitals and the Kohn-Sham energies. Of course, in order to make it practical, you have to choose the basis that you are going to use in order to make the expansion, in order to write these Hamiltonian and overlap matrices.